we're going to do another derivation of relativistic mass, or the first derivation, depends upon the order in which you're watching these. So I'm going to have, in my S frame, I have an I hat to the right and J hat up. Other times I'll refer to horizontal positive X to the right and positive Y up in the math brainwashing form. And so initially I have some mass m that is traveling vertically, or traveling in the J hat direction at some speed u sub 0. And so my initial velocity is u sub 0 j hat, where u sub 0 is almost 0. It's not quite 0. It is moving some, but it is small. It's much less than c, so I'm not worrying about any relativistic effects. Now, if I apply a force in the positive x direction, in other words, in the I hat direction, then this object is going to start out, and then it's going to start to accelerate in the I hat direction, and the path will look something like this. So we start out with some mass m sub 0, and we end up with some mass m. Now, we are working with an assumption that the mass is going to vary with the speed. And if it doesn't vary, then we should end up with m is equal to m sub 0. Now, at this point, when the force stops, we have some x component of the final velocity in the I hat direction and some y component in the j hat direction, which I'm also going to just let the x component be v and the y component be u. So my final velocity, vx I hat plus vy j hat, or v I hat plus u j hat. And I'm also going to assume that this force is applied long enough so that the speed in the horizontal direction is significantly larger than the speed in the vertical direction. I know that just basically starts out classical mechanics that force is equal to dp dt. And since my force is in the I hat direction, I'm just going to label that as fx I hat, which is just the derivative of my momentum broken up into components, an I hat and a j hat component with respect to time. And so I get I hat dpx dt plus j hat dpy dt. And so therefore, since this and this are equal to each other, my I hat component should line up and my j hat component should line up. So f of x is dpx dt, and 0, which is the j hat component of force, is equal to dpy dt, and therefore py must be constant with respect to time. All right, so in the S prime frame, S prime, the velocity of S prime with respect to S is just v in the I hat direction. And so we're, in essence, moving however fast the particle is moving at the end in the S frame. And so we end up with my final velocity is equal to u prime j hat. And my initial velocity is negative v I hat plus u naught prime j hat. And that's because in the S frame it's u naught, and now we're in the prime frame, so it's u naught prime. And here it starts out at u in the S frame and u prime in the S prime frame. So in the S frame, since py is constant, my initial is equal to my final value, so that's m naught u. Naught is equal to mu. Going back over into my S frame here, so mass times the velocity in the y direction, so I have m naught u naught, which is my initial velocity in the y direction, is equal to mu. And in the S prime frame, again, py is constant, so we have m u naught prime is equal to m naught u prime, because again, at the end of this, it is traveling so slowly, we're basically at the rest mass. If I then take my equations here and I take this divided by that, I get m naught u naught over m u prime naught, and over here I get that divided by this, which gives me mu over m naught u prime. Just breaking this up into a product of fractions, the left-hand side, just multiplying the m's and the u's, and then m times u's on the right-hand side, and then bringing the m's together. So I'm going to multiply both sides by m over m sub naught to get m over m sub naught quantity squared, and then multiply both sides by u prime over u, and we end up with this. Now realize that u is perpendicular to the velocity. So we need to deal with relativistic velocities perpendicular to the direction of the frame movement. And so Vy is equal to U naught, Vy prime is U naught prime, and Vx is equal to 0. Please refer to the other video to understand why we're doing this. But Vy prime is equal to Vy over gamma 1 minus Vvx over c squared, where V here, that's the velocity of the s prime with respect to s. And since it's perpendicular, U naught prime is just U naught over gamma times 1 minus 0. Again, refer to the other video. So U naught prime is equal to U naught over gamma, or gamma is U naught over U naught prime. After the interaction, we have this setup right here where Vy is equal to U, Vy prime is equal to U prime, and Vx is equal to V. And so U prime is equal to U over gamma 1 minus Vv over c squared. And that eventually boils down to U prime over U is equal to 1 over gamma 1 minus beta squared. So we take these two equations here, and we plug that into the equation we had here. So we have a relationship of the U naughts and of the U's. So from the other equation, we had m over m naught squared, quantity squared, is equal to U naught over U naught prime times U prime over U. And that's going to be equal to gamma. There's my gamma. And this is equal to this. And we end up with 1 over 1 minus beta squared, or m over m naught, is equal to the square root of this, which is just gamma. And therefore, the mass is equal to gamma times m sub naught. And there we go. Yet one more derivation of the exact same thing.